Hi everybody, welcome back to my channel on Feynman integration. Today, like I said in my last video, we're going to be re-evaluating the same integral yet again using a different method. So the method we're going to use this time is we're going to get that integral out. Well, let me just show you. Let me just show you how we'll get the answer this time. It's difficult to explain. It's difficult to give a Cliff Notes version of it. But basically, we're going to refer back to example 25. Go ahead and watch that video, and you'll see how we arrive at the next step. Anyway, as part of the process of solving the integral from example 25, we found this out. We found out that some function of t, if some function of t is equal to the integral from 0 to infinity of the inverse tangent of tx over x times x squared plus 1 dx, then that function of t will also be equal to pi times the natural log of t plus 1 over 2. Again, check that video out if you want to see why that's true. That's just one of the steps in evaluating the integral from example number 25. So we know this. We know that this is true. Well, it's true from 0 to infinity. It is not true for the negative numbers, as you can see, because you would end up taking natural logs of negative numbers, and that's a no-no unless you're dealing with complex numbers, which we're not in this case. So we're just going to leave it at that's true over the interval t is equal to 0 to positive infinity. It includes 0. Obviously, it does not include positive infinity because that's not a real number. Anyway, for our next step, what we're going to do is we're going to use the Leibniz rule backwards. Basically, since you can take a derivative of f of t with respect to t by taking a partial with respect to t of the integrand, you can take an antiderivative with respect to t by taking an antiderivative. I guess you'd call it a partial antiderivative, although I don't know that's what it's called. I'm just kind of making that up. An anti-partial derivative or partial antiderivative with respect to t of the integrand. What you get if you do that is you'll find that f of t, if you anti-differentiate this part, you'll get that big F of t is equal to this. And I'm skipping a lot of the work because it's not that difficult. The only part you really need to anti-differentiate is a tangent inverse, and that's messy, but it's definitely doable. Also this one. I'm sure you've all taken antiderivatives of natural logs before. It's messy, but it's doable. So what you get if you do that and then do a lot of rearranging and rewriting is this. That big F of t is equal to that. And also it's equal to the antiderivative of this part right here, which is written right here. So we have f of t equal to this, and we also have big F of t equal to this. And don't forget, you have to put the plus c since you're taking an indefinite antiderivative. So you need the plus c. Okay, so now we have to get rid of that c. We need to find out exactly what that c is equal to. Well, we can do that. Basically, we know that this is equal to this plus c. And that will hold for all values of t. So we need to find a value of t so that one side will cancel out, and the value you pick is 0. Because if you put 0 in for here, to here, you will get 0. And if you put 0 in for t here, you also get 0. Giving you that 0 is equal to pi over 2 times 1 times, let's see, that would be negative 1 plus c. In other words, 0 is equal to negative pi over 2 plus c, giving you c is equal to pi over 2. So that's how I got that c is equal to pi over 2. I'll just write it right here. pi over 2. And my black pen was running out of ink, so I had to do this in red. I hope it's showing up okay. If it doesn't, I'm going to redo the video. But if you're listening to this, obviously, I did not redo the video. Okay, so we've gotten this far. We've gotten that this expression is exactly equal to this expression right here. How's that going to help us? Well, if we plugged in 1 for t, you could see we could recover a negative 1/2 I. If this t was 1, you would square it and it would just become a 1, giving us natural log of x squared plus 1, which is exactly match our I. So that's what we're going to do. We're going to plug in 1 for t on for both f of t's. And what you do if you get that is that big F of 1 is equal to the integral from 0 to infinity of the inverse tangent of x over x times x squared plus 1 dx. And we note that that is exactly our little f evaluated at the point 1. And we have minus 1/2 I. And how I got that was that if you plug in, which we're plugging in 1 for our big F of t. So you get minus 1/2 of this part at t evaluated at the point 1, which is exactly I. So big F of 1 is equal to little f of 1 minus 1/2 I, and that in turn is equal to this part when you plug in t is equal to 1. And what you get if you plug in t is equal to 1 into that is that it's pi natural log 2 minus pi over 2. You plugged in 1, that would become a 2, canceling that 2, so you'd get pi natural log 1 plus 1, which is natural log 2, minus 1, and then plus a pi over 2, and work it out, this is what you get. So, now we're this far. We have that f evaluated at the point 1 minus 1/2 I is equal to pi natural log 2 minus pi over 2. Well, what is f evaluated at the point 1? Well, it's equal to that, and it's also equal to this, so that would be pi natural log 2 over 2. So, we have pi natural log 2 over 2, which is f of 1, minus 1/2 I is equal to pi natural log 2 minus pi over 2. And from there, it's extremely easy to solve for I. And what you get if you solve for I is that it's equal to pi minus pi natural log 2, which is what we got the last 2 times we evaluated this integral. Well, there you go. That's the third way to evaluate that integral, and hope you enjoyed that.